Hello, I am Grégoire Pichon from ATO's HPC Software R&D. After working several years on Lustre, I am now in charge of the NIC software stack for BXI, the Boole Exascale Interconnect. The portals for LND that allows Lustre to run over BXI has been used in the field for 3 years now. In this talk, I will present what work has been carried on during these 3 years. What has been improved in the portals for LND? What additional LNet features have been supported? What integration and packaging issues appeared? How production clusters with Lustre over BXI have been performing? But let's start with a brief LNet and portals for LND introduction. The Lustre network layer ensures communication between Lustre clients and Lustre servers. It provides routing between different networks through the Lustre routers. LNet allows to configure several routers to access another network. It provides high availability and recovery functions to handle router failure and restoration. LNet now allows to configure a node with several interfaces in the same network. In that way, it provides high availability and aggregation between these interfaces. LND stands for Lustre Network Driver. It provides LNet message transport for a specific network hardware like InfiniBand, Ethernet, or BXI. What are the requirements of an LND? First, it needs to register to LNet and provide function pointers through LNet LND structure. This allows LNet to rely on the LND to start up network communications on a new interface, or to send a message to appear in the same network, or to query the status of a peer. In turn, the LND calls back LNet to pass a message received on the link and check if it matches a target buffer at LNet layer. In that case, LNet calls LND receive and provides receive buffer address so that the LND can copy the data and complete the reception with the RDMA operation. Additionally, the LND calls back LNet with routine like LNet finalize or LNet set reply message lengths so that LNet can generate completion events with accurate information. Let's have a look at the portals for LND. BXI is the interconnect network developed by Boole. It includes a 48-port switch and a 100 gigabit per second NIC. The NIC provides an hardware implementation of Portals for Communication API. As shown in the diagram, the PTL4 LND release on Portals for Network API. This is similar to the SOC LND that release on TCP/IP communication stack. Portals for LND uses PTLF as network name and builds the LNet address from the BXI network ID. In the example, we have a node with two BXI interfaces with network ID 42 and 43. We declare that BXI0 device will be used within PTLF2 network and BXI1 device will be used in PTLF6 network. As a result, the node has 42 at PTLF2 and 43 at PTLF6 LNet addresses. The Portals for LND supports immediate and RDMA transmissions, peer state management, and flow control with transmission credits. For more details on the PTL4 LND, you can have a look at my LAD17 presentation describing internals of the portals for LND. What has been improved in portals for LND during these last 3 years? The first improvement deals with performance. We updated the LND to use distinct network channels for bulk I/O data transmissions. This allowed to reduce list matching overhead and to spread receptions on several list match engines. The second improvement is on performance also. The LND implements worker threads to handle received message passing, receive buffer reposting, and transmission finalization. The worker threads have been redesigned to improve parallelism and take NUMA binding into account. This optimization mainly improves LNet IOPS performance and depends on the platform architecture. The third improvement is about robustness. Situations from the field showed that the LND could have to handle unexpected or malformed messages and unexpected portals events. Therefore, we improved reliability and robustness of the LND in order to ignore inconsistent messages or events. The fourth main improvement was to support the support of ARM platform on the porting of the LND on AH64 architecture. This implied handling 64K pages. Running PortL4 LND on ARM requires BXI v2 hardware. The Portals for LND has been enhanced to support LNet features that appeared in Lustre 2.10, 2.11 and 2.12. These features are basically LNet multi-rail and LNet health status. But what does that mean for the LND? It must report to LNet when an interface goes down and goes back up. When interface is down, LNet does not even consider sending the message to that interface. It must also report to LNet the detailed transmission status so that LNet can build an health value for each interface and use it for its interface selection algorithm. I have shown here the various health status and their corresponding LND situations. The local timeout status is reported when transmission is stuck in LND send queue for too long, due to missing credits or hello handshake hug with a new peer. The local error status is reported by the LND when its resources are exhausted, missing transmission descriptors or unable to allocate new peer in the peer table. The remote dropped status is reported to LNet when the response from the remote LND indicates that LNet did not find a matching HEMI. The remote error status is reported when the remote peer LND resources are exhausted, or when the peer is unreachable through the fabric. And finally, the network timeout status is reported when the transmission is stuck in the LND active queue for too long. What is the LNet performance in a multi-rail configuration? This has been evaluated using a FAT X808 server with 8 BXI devices connected to 8 client nodes with one BXI device each. We compared the performance of the multi-rail configuration with the multi-net configuration where each BXI device of the FAT server is configured in a distinct PTLF network connected to one of the client nodes. We can see with blue and red lines that when increasing the number of clients, the multi-rail aggregated LNet bandwidth scales up to 45 GB per second. This is good, but it requires further analysis since we should be able to reach 70 to 80 GB per second as shown by the multi-net configuration in gray and yellow dotted lines. Let's talk now on Portal for LND integration and packaging issues. Portals for LND uses numeric addresses contrary to the SOC LND and O2IB LND that uses IP addresses. This is properly handled at kernel side with the libcfs netstring function in direction pointer table that differentiates numeric and IP addresses. Unfortunately, at user side, the libLNetConfig library does not fully support LNet addresses with numeric address ports and interfaces identified by a numerical string. For example, LNetCTLNet add command was failing when specifying a zero interface. This has been fixed with a patch I submitted to the community, but we recently identified that the YAML import needed also a fix. There is another issue with the -- gateway parameter of the LNetCTL root add command. The parsing of the gateway addresses with numeric address is not correctly supported at the moment. This will be reported to the community to improve integration of the portals for LND. Another point that would need improvement is LND packaging. Take the example of Lustre packages configured with O2IB built against Mellanox offhead, and a target cluster containing nodes with IB adapters and other nodes with Ethernet or BXI adapters. Quite surprisingly, the installation of Lustre requires Morphet packages to be installed due to symbol dependencies, even on nodes with Ethernet or BXI adapters only. Why should we have to install Morphet on nodes that have no IB hardware? Sébastien Pichon posted a patch that allows to optionally package LNDs in their own RPM. This limits the dependency on third-party network packages to the LND RPM. This LND RPM can then be selected by the cluster administrator to be installed or not on the nodes of the cluster. If you specify the -- which separate LNDs equal auto-IB, this will allow to include the auto-IB LND in a separate RPM named kmod Lustre LND auto-IB rather than including it in the kmod Lustre RPM. Additionally, having LNDs packaged in their own RPM would allow to build an LND against several versions of third-party network packages and provide this RPM in the same Lustre package set. Now let's have a look at clusters running Lustre over BXI. The first one I am presenting is T1K cluster at CEA, which was installed in 2018. It's now running with Red Hat 7.9 and Lustre 2.12.6. The cluster is made of 30 groups, where each group includes 276 Xeon Phi KNL clients and 5 Intel routers. Routers allow accessing servers as gateways from BXI to IB networks. A similar installation is running within Jolio Curie cluster at TGCC. Note that the routers are attached to L1 switches with cable lengths from 10 meters to 25 meters. And this had a consequence on the performance we're going to see in the next slide. The clients are configured to reach O2 IB networks through 5 routers. This is the 1, 2, 3, 4, 5 at PTLF route defined, and the check router before use and the live or dead router check interval parameters ensure HA and recovery. The peer discovery and health sensitivity features are disabled. The LNet bandwidth between one client and one router depends on the link length between the router and the switch and reaches 6 to 8 GB per second. The resulting Lustre I/O bandwidth for a group of clients is around 32 to 40 GB per second. The second cluster is Romeo at Université de Reims Champagne-Ardenne. It was installed in 2018 and now runs Lustre 2.12.6. The cluster uses a single BXI fabric connecting 4 Intel Skylake cluster servers and around 120 clients. 2/3 of the clients have 2 BXI devices and 4 GPU accelerated boards. The third cluster I present today is Hexa1 HFI at CAA. It has been installed in 2021 with BXI V2 hardware. It currently runs with Red Hat 8.3 and Lustre 2.12.6. Clients and routers are AMD nodes with a ratio of 576 clients to 4 Lustre routers that provide access to IB network and Lustre servers. The LNet configuration is very similar to the T1 key cluster, except for interface binding at LNet level. In a group, the LNet write bandwidth reaches 35 GB per second using only one interface per routers. The configuration and tuning will be updated soon to use the second BXI interface with a multi-rail setup, allowing to double the LNet bandwidth to the Lustre servers. As a conclusion, we have seen that Lustre over BXI is running and performing well on HPC production clusters with various hardware configurations. The integration effort of the portals for LND within Lustre sources needs to be carried on so that usability reaches the same level than other LNDs. The portals for LND will continue to be updated and tested with the new LNet features of the latest Lustre versions. Thanks for your attention.